we go. All right, so again, I'm using a slightly different setup, so if you have any trouble hearing or anything else, please let me know. All right, so last class, or I guess 2 classes ago, back before the exam, we had started looking at chapter 7 and 8, and we were doing things like calculating the wavelength, calculating frequency. Any questions from way back when we had started out chapter 7 and 8? All right, so let's keep moving forward. So here's a note about what you're going to be given on tests and quizzes. So you're going to be given the speed of light, Planck's constant. You will be given the relationship between joules and kilograms times meter squared per second squared. You never need that relationship, but you might want it just to help remind you that whenever mass is going into an equation with joules, your mass has to be in kilograms. Also, here's angstroms to meters, and something we haven't used yet, but it's called the Rydberg constant, and it is right at the bottom, and we're going to take a look at that today. But any questions on this page? Oops, I hear that I am breaking up. Let's see if there's anything I can do about that. Let me see. If I talk a little louder, is this any better? Good? Okay, perfect. I can always move the mic around. Right now it's actually slightly behind the monitor. I keep trying new setups to try to make it work better. Okay. But thank you for letting me know, Tasso, and if that ever happens, please either unmute and yell at me or type into that group chat. All right, so here we're looking more at quantum mechanics, and here are the basic ideas of our quantum mechanics. And first off, electrons are quantized. So you've probably heard of quantum physics, and that kind of freaks people out sometimes because they think that's a big, scary word. But what I'm going to show you is what quantum really means, especially for us in chemistry. So here we have a ladder, and I like to think of quantum chemistry and quantum in general as climbing the ladder. So I'm going to do a really bad job of drawing a person on this ladder. So there's my stick figure person, and that person can be at n equals 1, which we're going to call the first rung of the ladder. However, they can, in this case, jump to n equals 2 and beyond the second rung of the ladder. So this is how you climb a ladder, and most of you have done this. And what you also know is that you cannot, or at least most of us cannot, hover in between the rungs on the ladder. So you can be on the first rung, you can be on the second rung, and you can jump or step up, for most of us, between rung 1 and rung 2, but you can never just hover mid-air unless you have like a jetpack or anti-gravity shoes. You cannot hover here. And that's what quantum's all about. So the idea of quantum energy, quantum electrons, is that they have a place they need to be. They could be in the first energy level, or they could jump up to the second. But there's an area where they cannot hang out, and that is between the energy levels. Just like we cannot hang out in between the rungs on a ladder without a jetpack or anti-gravity shoes, neither can the electrons. So now let's get rid of my poorly drawn human and put a little electron here. So here's the electron, and it can jump up to the second energy level. So it can be in the n equals 1, and it can be in the n equals 2. Where it cannot be is just hovering here. It cannot hover in between the rungs. And that's what we mean by quantum. There is, the electrons can be at a certain energy level. They can jump up to the next one, but they cannot hover in between the energy levels. And again, that is what we mean by quantum or quantized. So I know that's a big concept. Any questions on that idea of quantum, that there's a place the electrons can be, but they cannot be in between those places? All right. So we have actually taken a look at this once upon a time when we looked at the flame test video. And again, I apologize, I couldn't do a flame test for you in person. But the idea is that electrons have a place where they normally are at, and that's something we're going to call the ground state. And when we do electron configurations, we will find the ground state of these electrons. Where should they be when they are lounging around on a Sunday afternoon? However, they can become excited and jump up to a new energy level. So just like, you guys, get really excited because it's almost time for chemistry class and you jump up, the electrons jump up as well. But what we just learned is they have to jump to a new energy level. They cannot hang out in between the energy levels. Then later on, they will relax or fall back down. So if you think of them as physically jumping up in the air, just like you do every time you think of your chemistry class, you will eventually come back down to the ground. You cannot hover mid-air. These electrons cannot stay in that excited state. They cannot stay in an energy level that they don't belong in. They belong in their ground state, and they can only be excited for a brief moment. When they relax back down, they need to give back the energy. So when we said they were excited because they took in energy. So this energy here looks like it's in the form of light, but there's a lot of ways that we can give electrons energy. So we can put them in a Bunsen burner like we do in a flame test. We can light them up with gunpowder like we do in our fireworks. We could plug them into electricity like we do for a lot of our lights. So we can give them energy in some form and it causes them to jump up. But when they relax, they give us back that energy, and that energy we see as a light emission. And this is what you saw in the flame test video. It's also what you see every time you see a fireworks. So we light those up with gunpowder, give them lots of energy. Not only do they fly up into the sky, but the electrons get excited and they jump up. And then what we're seeing is them relaxing back down. The color you see in the fireworks depends on how far they relax. So sometimes they relax very slowly, so one step and then another step and so on. And that's going to give us a very low energy light, so something like a red color. However, sometimes they're going to fall 2 or 3 energy levels. They have a huge fall. It's going to be associated with a lot of energy, and it's going to give us a high energy color like purple or violet. So this is what was going on in the flame test that we saw on video. And again, every time you see fireworks, this is what's happening. So it's actually kind of cool to know what's going on in the fireworks. Next time, social distancing is a memory and you're sitting out with your family, you're watching the fireworks, you're like, hey, everybody, let me tell you about how fireworks work. They will love you. They will think you are so smart, because you are. All right. So here is everything I was talking about in words. So an electron can absorb energy and jump from its ground state, where it's supposed to be, to that excited state. Then it's going to relax back down, and it always relaxes back down. It can never stay in that excited state. So it's going to relax back down, and when it does, it releases this energy. And it's energy in the form of light. And so when we see these bright lights, these colors, what we're seeing is that relaxation. We're seeing them give back the energy. So any questions on anything here? All right. So the first person to kind of figure this out was Niels Bohr, and he had this Bohr model, and we've later found it wasn't entirely correct, but it gives us a really good model for understanding what's going on. Let me just move this off the screen for a minute. Okay. All right. So here is a hydrogen lamp. So what's going on is inside of this lamp here, we have H2 molecules. And this lamp will be connected either to an outlet or it will have a battery. Usually it's connected to an outlet, so it has its cord. And I know, very bad electrical cord. But usually that's how it's connected. And so it's through electricity that we give it the energy to light up the electrons in the hydrogen. They're going to jump up and then fall back down. When they fall back down, they give us, I'm going to use pink here, this pink light right here. And then what we do is we pass it through a slit and then through a prism. And what the prism does is it separates the light, because even though to us This lamp looks like it's giving off pink light. Hydrogen itself doesn't actually give us off pink light. It actually gives us 3 or 4 lights. And I say 3 or 4 because usually if you're actually trying to look at this through a spectroscope, you see 3, but there are truthfully 4 there. And so these colors right over here, we have red, we have blue, we have sort of a blue-green, and we have a violet. But again, normally we only see 3 of those if we're actually looking for them experimentally, but we do know that there are a total of 4. So there are 4 colors, and what you're seeing right over here is just an average of those. We find that the majority of the electrons make a very short fall in hydrogen, so we get the majority of our light in the form of red, and that's why it looks more pink than blue or purple. But all of these colors right here are present every time we light up our hydrogen atoms, and these are considered a fingerprint. So if you didn't know what element you had, and you were able to excite them, pass the light through a slit and then a prism, and you saw this particular spectra, and you saw these exact lights here, then you could positively identify it as hydrogen. And you might be thinking, well, hey, that's a lot of work to figure out that it is hydrogen. Why would we go to that much effort? So in a little while, I'm going to be showing you a spectrum for some of our other elements. And one of the great things that we can do with this is, first of all, put this whole thing inside of a telescope and hook it up to a computer. So you don't have to hook up all the pieces individually. But then we can direct this at stars and other planets. And from those other planets, we get this fingerprint. So then the computer analyzes the fingerprints, and we can tell which elements are on these other planets or on these stars through this process here, just by looking at what fingerprint is coming off of the light from those other planets and those stars. So that's one way that we actually know what elements are on the other planet, which is super cool. But let's go ahead and talk about what we call the Bohr orbits. So these are our energy levels, and we're going to be using N to represent energy levels throughout the chapter. And I see my L here kind of got cut off. Energy level. All right, so N is going to represent our energy level, and the energy levels are quantized. So remember those rungs on the ladder. An electron can be in N equals 1, or it can be in N equals 2, but where it cannot be, is this area right here in between. So again, that electron could be hovering around and hanging in the first energy level, or it can be hanging in the second energy level. Oops. There we go. So it can be in the first energy level and it can be in the second energy level, but it cannot be between energy levels. Of course, I see Tasso, I see your question. Let me get to in just a moment. So of course the electrons do need to pass through this area. So the electron needs to jump to get from the first to the second energy level. However, they are not going to hover in the middle there. Just like you are climbing that ladder, you pass through the empty space, but you cannot hover there. And I see from Tasso, a prism separates the light. And yes, that's exactly what it does. It's going to separate the light that we see, which in the case of hydrogen was the pink over here. It's going to separate it into its component colors, and that's how we're going to be able to determine our spectrum. All right, so we were talking about quantized. So again, the electron can be in N equals 1 or N equals 2, but it cannot hang out in between. And that's what we mean by quantized. Now, a minute ago, I said N represents the energy level. That is true, but there's another name that we give to N, and it's something we're going to go into a lot of depth on, and that is called the quantum number. So in this class, we're going to be talking about quantum numbers, and they're sort of like coordinates, like on an XY plane. If you've done any graphing in a math class and you've said, hey, this point is at X equals 2, Y equals 4. we're going to be given coordinates to our electrons, and those are called quantum numbers. So n does represent the energy level, and later on we will call n the quantum number. It will be the first of 4 quantum numbers that we deal with. But any questions here so far about anything including the electrons jumping up, or the idea that these energy levels are quantized, meaning that you cannot hang out in between energy levels? All right, so here's another image of that Bohr model of the atom. What we know is that when we excite electrons in hydrogen, they jump up. So some of them will jump from the first energy level up to the third. Some will jump from the first up to the fourth, and some will jump up to the fifth. Now the ones that fall only a short distance, those result in red. Red is the low energy color. This one here falls sort of a medium distance, and this results in the blue-green. And this one here is falling a further distance, and that results in the violet color. So the way I remember this is I think back to that analogy of the ladder. Now, if you were on the first rung and you fell, you might sprain your ankle, it would hurt, but nowhere near as bad as if you were near the top of that ladder and you fell. That would be a lot more painful because there's a lot more energy involved. So falling a large distance is going to involve a lot more energy, which I translate as a clumsy person into a lot of pain. So here, the way I think about it is the further they fall, the more pain these electrons are going to be in, the more energy is going to be released. And so if we think about our light spectrum, we see our high energy here and our low energy over here. So the further they fall, the more likely you're going to see a high energy color like violet, and the shorter the fall, the more likely you're going to see a low energy color like red. So even though in the sky when you see those red fireworks, those are usually strontium and they look beautiful, and you think, oh my gosh, they have a lot of energy, that's actually the low energy color. All right, so there's a little disclaimer here about Bohr. He was amazing, but he only accurately predicted the hydrogen spectrum. So there are many more models of people who did things after Bohr for other atoms, but Bohr did a great job with hydrogen. Not so, his model didn't work quite so well with some of the other atoms, but that's okay. Gave us a really good foundation to study what's going on inside of the atom. But any questions so far about what's going on? I see. Is this like a flame where violet is hotter than red? Yes. So violet is hotter than red because it's a higher energy color. Yes. So it indicates there's more energy involved. Yes. Exactly. All right. So other questions? Good question, Clinton. So are electrons spherical? We model them as being spherical. Yes. Whether they truthfully are or not, I'd have to look up, but that's the way we model them. So if you were to see them in a textbook, they would be modeled as spherical. All right, so other questions so far? All right. So here we're going to do a calculation with a Bohr atom, and we're going to use that constant I mentioned a minute ago. This is the Rydberg constant. And this is going to be given. So how much energy is released when an electron falls from the n equals 3 level to the n equals 2 level of a hydrogen atom. And here is our formula. And again, I'm going to give you the formula. And here delta E represents the change in energy, final minus initial. Our H is going to be our Rydberg constant, and we have 1 over N2 final. So that's our final energy level squared, minus 1 over N2 initial, which is our initial energy level squared. All right, so let's start off by writing our formula. We have our delta E equals RH times 1 over, I'm going to say N2 final, so my F there is my final, minus 1 over N2 initial. All right, so here we're asked to find the energy. So that is delta E. Next step, we're going to put in our Rydberg constant. So negative 2.18 times 10 to the negative 18 joules, like so. Now I have 1 over my N final squared. So let's take a look and see what our final energy level is. So it fell from the third energy level to the second. So the second one right here is going to be our final, because that's where we're falling to. And the third energy level will be initial. Because we're falling down, we started at a higher energy level and we're falling down to a lower energy level. With this equation, you're always going to be going down. So you're always starting higher and going down to a lower level. All right, so our final was 2. So I'm going to say 1 over 2 squared minus, now I need that initial energy level, which we said was a 3. So it's going to be 1 over 3 squared, like so. All right, so I want to do the calculation with you because there's a lot of algebra in here, or I guess a lot of arithmetic in here, but any questions on how I set things up and how I decided which one was the final energy level, which one was the initial energy level? All right, so let's take a look at our calculator. All right, what I want to start off with is this right in here. This is where students often get confused in the calculations. So what I'm going to do is use negative exponents. So if you use a negative exponent, it means you're down in the denominator. So I'm going to say 2 to the exponent negative 2. So a 2 to the exponent negative 2 is the same as saying 1 over 2 squared. So let me prove that to you. Here it says 0.25, and if I did 1 over 2 squared, it is also 0.25. So again, whenever you put a negative on your exponent, you're just saying that exponent is down in the denominator. So let's give this a shot. So 2 to the exponent negative 2 minus 3 to the exponent negative 2. So what I've just entered is this part right here. So I know this is kind of a weird way of entering it, and if you're not comfortable with it, you don't have to use it, but I find it makes your life easier, and I have a lot of people who end up making mistakes on this part of the calculation, so I just wanted to give you this way of doing it. In case you wanted to try this, it is an easier way to do it, but I know it gets a little funky with those negative exponents. But any questions on how I entered this? Okay. So after that, I'm just going to multiply it by negative 2.18 times 10 to the negative 18. And it looks like our delta E, and I'm going to go ahead and do this to 3 sig figs. I'm going to say negative 3.03 times 10 to the negative 19, and our unit here will be joules. And just to make a note about sig figs, these two numbers are energy levels, so they are exact. Okay, any questions on how I calculated this or anything else? So I'm going to take a screen print of this just in case you want to look over the calculation later. All right, so questions about anything that we've done here with this problem? All right, so we have calculated the energy, but just to be more complete, this is the energy per photon. So each photon of light gives out this many joules of energy. And this negative right here indicates the direction. So this is always given out energy. So something that gives off energy. Anybody remember what we would call that? Yes, excellent. See lots of exothermics coming through. So anytime an electron falls down, it's always giving off energy, therefore it will always be exothermic. All right, questions on anything here so far? Okay, so Jervin, go ahead.
So I saw two equations for energy change. One was energy final minus energy initial, and the second one was energy equals RH times, and then those fractions. Mm-hmm. How did you know which one to use?
So you're saying that you saw another equation where you had the initial before the final, right?
Yeah. So since there's two, does that mean there's like two ways to find the energy change?
They're actually the same equation, just algebraically moved around. So let me show you how they interconvert. So here is the one that we've used, and we use the Rydberg constant. I believe that was 2.18 times 10 to the negative 18. But there's another way of doing it, and that other way of doing it would be delta E equals RH times 1 over N2 initial minus 1 over N2 final. But if you do that, then you have to use a positive Rydberg constant. So these are actually the same calculation. It's just here the negative is in the Rydberg constant, and here it's positive. And here, essentially these two are swapped. So when you swap them, you change their sign. So here you would get a negative answer, and then you have a positive here. And here you would get a positive and a negative. So it's just two different ways to do the equation. I like this equation up at the top because we do so much of final minus initial that I think this is easier, and this is the equation on the top that I'm going to give you. But the other one below, you see it in textbooks a lot, and it is a valid equation to use. But if you use it, make sure you use a positive Rydberg constant. But it's really the same equation, just moved around a little. Does that help a bit?
Actually, the other what's it called? The other equation I was thinking about was the like the one without the RH.
What is the other equation that you're looking at?
It's delta E equals E final minus E initial.
Okay, so E final minus E initial, right? Mm-hmm. Oh, okay, I'm sorry. So this equation right here, sorry, I went in a totally different direction. I thought you were talking about the other version of the Rydberg equation. Let me get all this out of the way. Sorry about that, just went on a tangent. All right, so this one is saying if you know the final energy and the initial energy, then all you have to do is subtract them.
Okay.
But this is if you are given that energy.
Okay.
Yeah. Sorry about that.
All right, no, that's fine. That makes sense. Thank you.
Yep. So just one more thing about this one is the way you would identify that you're using this equation is if you're given energy levels. So if you're given those n's, this is the equation that you're going to use. But you're right, if you were given final minus initial, if you were given final energy and initial energy, it's just the difference between those. Yeah. All right, other questions so far? All right, so next up it says, what is the color of light emitted? So if you know what transition the electrons went through, you can actually figure out the light that it is going to emit, which I think is super cool. Everybody thinks is super cool. All right. So here is our formula, and again, this is going to be given. So here we have our energy equals H, which is Planck's constant, which is again going to be given, times c, which is the speed of light, which will also be given, divided by the wavelength. So in our previous problem, we found energy, and now we're going to solve for the wavelength. Once we know the wavelength, then we can come up to the color wheel and see what color it is. Now, I don't expect you to memorize the color wheel. If I want you to find a color, I will give you that color wheel. So let's give this a try, and we're going to use the energy that we found here. And when we do this, we always want the simple answer to this. And I say simple answer because later on we're going to talk about what this energy would be like per mole. But what we want is the direct answer that pops right out of our Rydberg equation. And this is the joules per photon. So again, if you're trying to find the wavelength or the color, you want to just solve for that energy per photon, not per mole. Okay, negative 3.03 times 10 to the negative 19. And again, that is joules per photon. So now I'm going to do 3.03 times 10 to the negative 19 joules equals, and I'm going to put in Planck's constant, 6.626 times 10 to the negative 34. And the units are going to be joules times second. And then, for C, we're going to put in our speed of light, 3.00 times 10 to the 8th meters per second, like so. And down on the bottom, we're going to get our wavelength. All right, so any questions on anything here so far? All right, so I did something here that you've seen me do once a very long time ago, and that is I made a negative disappear. Your math teachers would gasp and faint a little bit if they saw me doing this. But remember that negative is just directional. It just tells us it's an exothermic reaction. We are going to be solving for a wavelength. So this is going to be measured in meters. There's no way to have negative meters. So if you add the negative in here, you'll end up with a negative over here because you don't have another negative to cancel it. So because I know my meters must be positive, I got rid of the negative now. But those of you who'd like to carry the negative through and then at the last step say, hey, wait, I can't have negative meters and get rid of it, that's fine too. But just remember your wavelength must always be positive. It's a measured value. It's going to come out here in meters. So any questions on that? I know it's really uncomfortable because your math teachers have like beat into you, don't drop your negatives. Okay. All right, so let's go ahead and solve this. So if I was to, put that green, I'm going to multiply the wavelength on both sides. It will cancel out. And if I were to divide both sides by the 3.03 times 10 to the negative 19 joules, on the left side, those will cancel out. So we're going to be left with our wavelength equals 6.626 times 10 to the negative 34 joules times seconds, like so. Let me clean up that 6. All right, times our speed of light. And down in the bottom, 3.03 times 10 to the negative 19 joules, like so. So any questions on how I did? Oh, where did I get the value of E? So E came from our previous problem, because this is actually part B of that previous problem. So that was this value right here. All right, so other questions on where I got numbers or how I set things up or how I solved it? All right, go ahead and take a moment and solve out for that wavelength. And this wavelength's going to come out in meters. Go ahead and type into the chat box when you get your value. And I see a few different numbers, but go ahead and tell me what it is in meters. So what's the first number you get out of there? Because I see a correct number in nanometers, but what was it in meters, the first thing that came out? All right, so I'm seeing 6.56 times 10 to the negative 7. How about the rest of you? Are you getting similar values? Okay, so it looks like Angie and Tasso got similar values. And I know one got a similar value and he just converted it into nanometers, which we'll do in just a minute. And I apologize for the sneezing in the background. That is my cat. She doesn't have COVID-19. She just has allergies, so she sneezes all the time. All right. So how's everybody else doing? I see 2 people or 3 people that got that answer. Anybody get something different or needs more time for calculations? Yes, no? Okay. All right. So 6.56 times 10 to the negative 7, and our unit here was the meter. So we are going to convert to nanometers, but any questions on anything so far here? All right, for those of you who want to see how things cross out, joules cancels with joules, seconds cancels with seconds, and so we are left with the meter, and that's where we get that unit from. All right, but one was right. We do have to convert into nanometers to find our color. So here I'm going to do 6.56 times 10 to the negative 7 meters. And for every 1 meter, there's 10 to the 9th nanometer, so it does end up being 656 nanometers, like so. So I went through that conversion kind of quickly, but any questions on how we're doing that conversion? All right, so 656 nanometers. So now we're going to go up here, and I'm just going to remind us, 656 nanometers. All right, so type into the chat box what color you think this is going to be. Excellent. So I see lots and lots of reds. Excellent. So here red starts at 6:30 and ends at 7:50. So somewhere inside of here would be 6:56. All right. Any questions on how we found the color or anything else here? All right, so what color is omitted? And it is red. All right, questions about anything we did here or in the previous problem where we found our energy? All right, so before we go on, I do want to show you one other alternative to finding the energy. So I'm going to write out another problem here, and I'm going to say that this is part C. And I'm going to say, what is What is the energy of this light per mole? So what I mentioned earlier is that when you calculate your delta E using that Rydberg equation, you are going to get your energy per photon. But sometimes it's more helpful to find the energy per mole. So we need to be able to convert into moles. So what I'm going to do way back up here is I'm going to go ahead and copy this. So where I'm getting this is from part A. So we're looking at the same problem as we did earlier. But here it is joules per photon, and we want it in joules per mole. So negative 3.03 times 10 to the negative 19 joules on the top, photons on the bottom. Now we're going to do a conversion, and it's a conversion you've done many times, but I don't think we've done it with photons before. So here I'm going to put photons on the top, and we're going to put moles on the bottom. And for every 1 mole, there is your favorite number of photons. You just have never seen it with photons. And that is 6.022 times 10 to the 23rd. Let's squeeze all this in here. All right, so 6.022 times 10 to the 23rd, Avogadro's number of photons. And we have a question, are photons the same as atoms? They are not. So a photon is a small particle of light. However, it works just like atoms when we're trying to find the moles. So once upon a time, I told you could have a mole of anything. You could have a mole of avocados, a mole of blueberries. But it's not realistic to think about that because a mole of blueberries would take up the entire Earth. So we normally don't talk about moles with large things, even though you may not consider normally a blueberry to be large. It is huge compared to an atom. But a photon is very, very small. It is smaller than an atom, and therefore we could talk about moles with our photons. So again, photons are not the same as atoms. They are just tiny particles of light. But we can talk about moles of photons because they're so small. All right, so any other questions about how we're doing this? All right, so photons are going to cancel, and we're going to be left in the unit joules per mole. But go ahead and take a moment and calculate out how many joules per mole we have. When you get your answer, feel free to type that into the chat box. All right, so I'm seeing a negative 1.82 times 10 to the 5th. Anybody else get a similar or different answer? All right, so it looks like we're getting lots of those answers. Excellent. Any questions on how we can convert between joules per photon and joules per mole? Okay, excellent. So just a reminder, if you're ever looking for the color or the wavelength, you only want joules per photon because it's each individual particle of light that is traveling at, in this case, 656 nanometers. Questions on anything that we did with this problem, part A, B, or C? All right, so now is probably a good time to take a break. So let's go ahead and take our break, and come back at 6 o'clock. And I will be here if you guys have any questions for me. Oh, yep, I hear. I see Angie got a question about summer class. Yep. What was your question, Angie? Actually, just gonna reach up and try to pause the video. If I can. Pause it. For some reason, the video doesn't want to pause. I'm just gonna go ahead and stop it, and then I'll start again.